Hi, I'm Park Jong-won. I will introduce intelligent beam training for millimeter wave communication via deep reinforcement learning. Introduction to system model, Markov decision process, and deep reinforcement learning, DRL-based beam training algorithm, numerical research, and conclusion will be presented in order. Introduction. Millimeter wave communication has attracted considerable attention owing to its large available bandwidth. Due to the propagation features of millimeter wave signals, it has strong straightness and large path throws. To overcome this issue, large-scale antenna arrays are used for beamforming. Considering the expense and the power consumption, millimeter wave communication systems usually adopt hybrid analog-digital architecture, where the number of RF chains is far less than that of antennas. In the past several years, different hybrid precoding algorithms have been proposed, and these algorithms rely on complete channel state information, which is, however, difficult to acquire in millimeter wave communication. So in millimeter wave communication, beam training is used to estimate equivalent channel vectors. It is used to find a beam pair of transmitter and receiver in the analog domain, like the figure 1. Exhaustive search-based beam training algorithms are time-consuming, and hierarchical search-based algorithms were mostly designed for single-user, single-stream transmission, and the training overhead is still very high in the system with large-scale antenna arrays. To reduce the training overhead, machine learning-based beam training algorithms were proposed. One category exploits supervised learning, which however requires a lot of training samples in advance. Note that collecting training samples is expensive and impractical for a dynamic environment. The other category is based on multi-armed bandit, and due to the simplicity of the algorithm, its ability to extract information and exploit it is limited. In this paper, they propose an intelligent beam training algorithm for multi-user millimeter wave communication systems by integrating beam training procedure and deep reinforcement learning. We first formulate the problem of beam training as a Markov decision process. Actions are designed according to the differences of beam indices. States are designed as consecutive images. The proposed algorithm can sense the change of the environment, requires no priori knowledge of dynamic channel modeling, and can train beams with negligible training overhead. System model. This is system model used in this paper. They consider a communication system which consists of one base station and multi-mobile users. Because millimeter waves are used as directional beams, it is difficult to cover a large area, and mobile users can move their positions. So beam sweeping is used. Beam sweeping is a technology that covers a wide area through beams that are sequentially transmitted and received at intervals and directions predefined. Through the beam sweeping, equivalent CSI can be obtained. However, sweeping the entire beam space in each time slot is still time-consuming. So in this paper, using DRL, it will be efficient. Markov decision process and DLL. Markov decision process, and let's call it MDP for short. As you know, MDP is defined by decision epoch, states, actions, transition probabilities, and rewards. In this paper, they formulate the problem of beam training as an MDP. DRL. If all elements of MDP are available, dynamic programming can be used. However, obtaining all elements is difficult and even impossible sometimes. To overcome this difficulty, the reinforcement learning has emerged. Q-learning is most well-known and widely used one, but it has limitation of computational memory capacity. So in this paper, DQN is used. DRL-based beam training algorithm. To integrate DRL and beam training, they started by formulating the problem of beam training as an MDP. This is an epoch. To avoid estimating channel vectors directly, beam sweeping is required to acquire the equivalent CSI. Due to the use of beam sweeping, a time slot is divided into 3 phases: beam sweeping, hybrid precoding, and data transmission. Action space. It is intuitive to define each beam as an action, but it is inefficient to sense the rate of change of the environment. An action is defined based on the difference of indices of the beams in 2 adjacent time slots, and the number of beams used for beam sweeping. For example, we assume that there is one mobile user and the number of available beams is 32. In the current time slot T, it is assumed that F10 is allocated to the mobile user. If the environment varies relatively slowly, F11 and F12 may be allocated to the mobile user in the next time slot T+1. And then A will be 2 and B will be 3. A and B depend on the rate of change of the environment. State space. The distribution of effective path or beam direction is described as image like A. Since single image is static, they define states by several consecutive images to capture the change of the environment like B. As shown in C, a compressed image is obtained due to sparsity, and it reduces the size and accelerates the convergence. Especially advantage of defining the states as images is that many advanced image processing techniques can be used. Reward function. They take the goal of maximizing system sum rate as design goal. The SINR can be used as performance indicator, and design goal is to maximize their log sum. Reward function is shown on the right side, and FT optimal is the optimal objective function value. Algorithm 1 is to maximize the sum rate of the system, and FT optimal can be obtained to use in algorithm 2, ESBT algorithm. In algorithm 2, the entire beam space is swept to initialize reference beams. By step A, action is executed, reward is computed, and analog and digital precoding vectors are obtained. And data transmission is accomplished. In step C, parameter of DQN is updated, and step D, go to next time slot. Repeat from A to D. Rewards were accumulated for every time slot and used to find the maximum reward value. Numerical result. Simulation environment is like figure 4. The two probability distributions on the right side, model 1 and model 2, are considered in order to probabilistically represent changing to another beam in the next time slot because of the change of the environment. The index difference 0 means that the current beam is used again in the next time slot. Model 1 is a model in which mobile users are relatively slow moving and mobile users of Model 2 move relatively faster. The matrix probability of successful alignment and average effective achievable sum rate, which is AEASR, are used to evaluate the performance of different beam training algorithms. For comparison, simulation results of the exhaustive search-based beam training algorithm, for short EXSEBT algorithm, and the hierarchical search-based beam training algorithm, for short HSBT algorithm, are also provided. It is observed from Figure 6 that EXSEBT achieves the highest probability of successful alignment. However, EXSEBT sweeps the entire beam space, which is time-consuming and may not be applicable if the channel or the environment vary fast. Although the probability of successful alignment of EXSEBT is a bit higher than that of ESBT, the gap between the two algorithms becomes negligible as SNR or the number of antennas increases. It is also observed that HSBT achieves the worst performances. The AEASR performances of different algorithms is shown in Figure 7. It is seen that ESBT achieves the best performances. It approaches the performance of OABT algorithm, and it can be seen as the optimal beams are provided without any training overhead. It looks like effectively reduces the overhead of beam training and reserves more time for data transmission. The advantages of ESBT becomes more noticeable as the number of antennas increases. Figure 8 demonstrates the AEASR performance of ESBT and EXSEBT for the two probability model. It is not surprising that EXSEBT achieves the same performance for the two models, but ESBT also achieves almost same performance for the two models. The reason for this is that although the average rate of change of the environment in Model 2 is larger than that in Model 1, the variance of change rate of the two models are the same. Therefore, the training overheads corresponding to the two models are the same as well. Conclusion. In this paper, they proposed an environment sensing-based mmWave beam training algorithm by integrating DRL with BTP. The proposed algorithm can sense the change of environment and intelligently adjust beam training strategy. Importantly, it does not require any priori knowledge of channel modeling and thus can be used in many complicated scenarios. And it is beam training algorithm with negligible training overhead. Thank you for listening.